So what is a projectile? A projectile is just an object that travels in both the vertical and horizontal direction under only the influence of gravity. So if I were to draw a little picture of what that would look like, let's say I have a ball in my hand and I throw it up on an angle. So I throw it up like this, let's say. So it has an x component here and it has a y component as well, going like that. Okay, so it's not just being thrown straight up. And it's not just being thrown horizontally, it's being thrown vertically and horizontally. So on an angle, what's going to happen to this ball? It's going to go up, and then eventually it's going to come back down and hit the ground. Right? So the shape that a projectile takes, its trajectory, is a parabola. And anytime an object is thrown on an angle and the only force that's acting on it is gravity, it's going to be a projectile motion problem. Okay, so there's some steps that I like to go through whenever I solve projectile motion problems. We'll go through the steps first, and then we'll practice 4 problems using these steps, and hopefully they'll all make a lot of sense to you once we've practiced some questions with them. Okay, so bear with me while we go through the steps. So step 1, the first thing that you want to do All right, so in step 1, the first thing that you want to do is draw a picture. And your picture should have an x and a y axis. So I'm just going to highlight the most important things here. We're drawing a picture. It's going to have an x and y axis showing the initial velocity vector of the object and the path that the object takes, so the trajectory of it, which would look like a parabola. The x and the y axes should lie along the bottom and left side of your picture. And the x-axis will point to the right, the y-axis will point up, and that indicates that those are the positive directions. Okay, so right will be positive, up will be positive. The next thing that you're going to do is make a table. The table is going to be divided into 2 columns, one that will say x, the other one will say y. And on the left side of the table, you're going to list all of the variables in the kinematic equations. And you're going to use all of the information that you put in your picture from step 1 to fill out the table. All right. In step 3, you're going to select the column of the table that has the most information. Okay, so one column will have more information than the other column. The column that has the most information, you're going to use a kinematic equation to solve for time in that column. Once you know that time, you're going to put it in the other column, and then you can solve for whatever is missing. Okay, so this will make a lot more sense when we actually practice the problems with it. And that's step 4. You're going to use the other column to solve for the unknown value. Okay, because now you know the time from step 3. All right, so just like in the previous lecture, you're given 3 kinematic equations. These are the same 3 kinematic equations you saw before. You'll be getting these on your tests and exams, so you don't need to memorize any of them. All right, so let's go ahead and use this process to actually practice some problems. So the first problem says a soccer player is running across the field towards the opponent's net. She kicks the ball towards the net with a speed of 14.7 meters per second and an angle of 28 degrees above the ground. How long was the ball in the air? So that means like how much time did the ball spend in the air? And what horizontal distance does the ball travel before hitting the ground? All right, so we're going to go through the steps that we described on the previous slide. I'm going to start off with step 1. So step 1 was draw a picture. And when we draw a picture, we're going to start off with the x and y axis. And they're always going to be drawn this way. X is pointing to the right, y is pointing up. And we want to draw the initial velocity vector. So the ball starts off at the ground. So here's the ball down here on the ground. And she's kicking the ball towards the net with a speed of 14.7 meters per second at an angle of 28 degrees above the ground. So that looks something like, let's say, something like this. This angle here is 28 degrees. This is the initial velocity, which is 14.7 meters per second. Now we want to actually draw the trajectory of the ball, so the path that the ball is going to take. So the ball is going to go up into the air and then eventually come back down and hit the ground. So it goes up and then comes back down, hits the ground somewhere here. Okay, now do we know any other information? So it says it's talking about a ball. We're going to assume the ball is on the ground. It's not starting up higher at all, so it's at the 0 position. We want to know how long was the ball in the air for, so that's delta t, that's the amount of time it spends before it hits the ground. And we want to know what the horizontal distance is that the ball travels. So we want to know what this value is right here when it hits the ground. So we can put in any variable we want for that. We can call it x because it's an x position, or we can call it d for distance. It really doesn't matter what letter you choose, but it's this number right here when it hits the ground. I'll just use a different number, different color so you can see it a bit better. Okay, so that is what we're solving for, D. All right, so that was step 1. Step 2 was to make a table. So the table is going to be divided into 2 columns, x and y. And then on the left side, we're going to put in all the variables from the kinematic equations. So I'll start with S initial, S final, V initial, V final, A, and delta t. So those are all the variables in the kinematic equations. Okay, now we're going to fill out the table. So S initial, let me just identify on that original drawing, this is the initial position, and this is the final position. Okay, so when I say S initial, I'm saying, what is the initial position over here? I want the x and the y component. If I want, I can label this as a point. So what would this point be over here? It would be at the origin, so it's 0, 0. And what about this point at the very end here? What is that? Well, the x component is d. We always start with x. And then the y component is 0 because it's on the x-axis. So those are our 2 points. That's our S initial and our S final. Now we're just entering that into the table under x and y. So S initial x component is 0. That's this one here. And S initial y component is 0. That's this value here. We can do that for S final. S final x is d. And S final y is 0. All right, so now we move on to V initial. V initial, we want the x and the y components. So right now, we have the hypotenuse, but we need to decompose it into x and y components. So let's try to do that in our drawing. So we have this vector and this vector. This is the V initial x, and this is the V initial y. Okay, so when we're looking for V initial x, the first thing you have to ask yourself is that the adjacent side to the 28 degrees or the opposite? Okay, so it's the adjacent side. So since it's adjacent side, using SOHCAHTOA, that means we're using cos. So our V initial in the x is going to be 14.7 cos of 28 degrees. And the V initial in the y direction, y is opposite of 28 degrees, so that means we're going to use sine. Okay, so I'll just write out SOHCAHTOA here. When you're looking for the adjacent side, you use cos. That's what we did when we looked for the x component of the initial velocity. When you're looking for the opposite side, you use sine. So it's going to be 14.7 sine of 28 degrees. All right, V final. That's the speed when it's hitting the ground again. We don't really have any information about that. We're just going to leave that blank. The question's not even asking us about that, so we're not going to put that in. A lot of people have a misconception that the final velocity is 0. So when an object hits the ground, it hits it and it comes to a stop. But when we talk about final velocity, we're not talking about what the speed is after it hits the ground and then comes to a stop. We're talking about what the velocity is as it's hitting the ground. So while it approaches the ground and is just at the point where it just hit it. So it's not 0. Okay, so I'm going to leave that blank. That doesn't mean it's 0. It just means that we don't really have information about that and we're not looking for that. So we're just going to leave that. Okay, acceleration. So this is a projectile. The only force that's acting on it is gravity, and gravity acts downwards, right? So the acceleration due to gravity points this way. And what is the value of that? The magnitude of acceleration is 9.80 meters per second squared. Okay, so there's our vector for acceleration. Now we want the x and the y component of that. So there is no x component because it doesn't have a horizontal component at all. It's just going straight down. So the x component is 0. And the y component, since up is positive, that's what this graph is implying. This arrow pointing upwards for y means that up is positive. So the y component of acceleration then would be negative since acceleration is pointing down. Negative 9.80 meters per second squared. Okay. The last value, the last variable here is delta t, time. We don't know that value, and that's what part A is asking us for, is time. Okay, so we've gone through step 1 and step 2. The next step now, step 3, is to choose the column that has the most information and solve for time. So I'm going to just write solve for delta t. So which column has the most information, the x column or the y column? So when we look at the x column, there's this variable here, d, that we don't know. And then we know the other three other values. In the y column, we know 4 values. There's no unknown variable other than v final, which is the case for both x and y. So y has more information than x does. So we're using y right now. We're going to solve for time using all the numbers in y, in the y column. Okay, so how do we solve for time here? We know s initial, s final. We know v initial. We know delta t. We know a, and we're looking for delta t. So delta t is our unknown. What is the one variable that we don't know and we don't want to know? It's v final, right? So v final is the thing we don't know and we don't want to know. So we're going to use the kinematic equation that doesn't have v final in it. That's the first one that looks like this. S final equals S initial plus v initial delta t plus 1/2 a delta t squared. And now we can sub in everything that we know. So S final, remember we're looking at the y column only. S final is 0 equals S initial is 0 plus v initial is 14.7 sine 28 degrees delta t plus 1/2. A is negative 9.80 delta t squared. All right, so now we're just solving for delta t. I'm going to simplify all of this and I'm going to put it in the correct order. So you can see delta t is written out twice. Once delta t, the other one delta t squared, which means we can factor, we can use the quadratic formula. I'm going to use the quadratic formula here. So I'm just going to rearrange this so everything is in the correct order. So I'll leave everything on the right side. First is the 1/2 times negative 9.80 delta t squared. Delta t squared always comes first, so that's negative 4.9 delta t squared. And next is the 14.7 sine 28 delta t. So I'm going to type this on my calculator. 14.7 sine 28 degrees. And I'm left with plus 6.901 delta t. This isn't my final answer, so I don't want to round too much, so make sure that you're not rounding this to 7, for example. That would be rounding way too much. So you just want to keep some extra digits there. All right, so now we're going to solve for delta t. We're going to use the quadratic formula, so let's identify our a, b, and c. So our a value is the number in front of the delta t squared, so that's negative 4.9. Our b value is the number in front of the delta t, so that's 6.901. And our c value is the number that's by itself at the end. There's nothing here, so it's a plus 0, so c is 0. So we're going to solve for delta t. Quadratic formula is delta t, because that's the variable we're looking for, equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now we can substitute everything that we know. Delta t is equal to negative b, so b was 6.901, so negative b is negative 6.901, plus or minus the square root of b squared, so 6.901 squared minus 4, a is negative 4.9, and c is 0. It all goes under the square root, all over 2 times a, which is negative 4.9. I'm just going to type this into my calculator. Once with a plus and once with a minus. I'll start with the plus. So negative 6.901 plus the square root of 6.901 squared minus 4 times negative 4.9 times 0 over 2 times negative 4.9, and I get 0. Now I'm going to do it again, this time with a minus. So I'm just going to change that plus sign to a minus sign. Okay, I'll just highlight which one I'm talking about. This plus sign that I had before, I'm changing it to a minus, so I'm doing this equation twice on my calculator. And this time I get 1.408. All right, so the question says, how long was the ball in the air for? So delta t is 0. That was at the beginning. The time was 0 at the beginning when I first kicked the ball, or the girl first kicked it. And then delta t, the time, is 1.408 when it hits the ground again. So the ball was in the air for 1.408 seconds. So that's the answer to part A. I'll just put a box around it so we know this is the correct answer. Okay, so now the question is asking in part B, what is the horizontal distance that the ball travels before hitting the ground? So it's asking for this d value here, right here, this horizontal distance that it travels, right there when it hits the ground. So this is going to take us to step 4, and in step 4 what we're doing is we're using the time that we got in step 3, but we're putting it in the other column. Okay, so the time we got from step 3, time is a scalar quantity. It's not a vector, so it's the same in the x and in the y direction. So in the y direction, we solved for time and we got 1.408. In the x direction, it's the exact same value, 1.408. Okay, so now we're going to move on to column x to solve for time. So that's step 4. So I'll write that down below here. We're going to solve for the unknown in the other column. So in this case, in the x column. All right, so we're looking at the x column. In the x column, again, the variable that we don't know and that we don't really want to know is v final. So we're going to end up using the exact same equation we used in step 3. So that is s final equals s initial plus v initial delta t plus 1/2 a delta t squared. And now we're going to substitute everything that we know. So S final, we labeled it as D, so that's what we're going to put in here, D, equals S initial is 0. Remember, we're only looking at this X column here. We're looking at the numbers in this column, plus V initial, which is 14.7 cos of 28 degrees, delta t we know what it is, 1.408 plus 1/2, our a value is 0, and then delta t squared, 1.408 squared. All right, so everything in this term goes to 0 because 1/2 times 0 is 0, and 0 times anything is 0. So now we can just type everything on our calculator, and we get d is equal to 14.7 cos 28 times 1.408, and we get 18.3 meters. And that's it. That's the answer to this question. What horizontal distance does the ball travel before hitting the ground? 18.3 meters. Okay, so this was the answer to part A, 1.408 seconds, and the answer to part B is 18.3 meters. All right, let's move on to question 2. So, standing on top of a hill, you aim your pellet gun at a target which is on the ground, a horizontal distance of 32.5 meters from the base of the hill. The pellet is fired with an initial speed of 125 meters per second at an angle of 7 degrees below the horizontal and hits the target. What is the height of the hill? Okay, so you're on top of a hill. Let's draw step 1. We're going to start with step 1, draw a picture. And our picture always looks like an X and Y axis like this. So we want everything to be in this quadrant here where X and Y is positive. So you're on top of a hill. So let's say you're here and you shoot or you fire your pellet gun with an initial speed of 125 meters per second at an angle of 7 degrees below the horizontal. So this is the horizontal here, horizontal line. 7 degrees below the horizontal would be something like this, where this angle is 7 degrees. Okay, so our V initial is equal to 125 meters per second. The pellet is fired with an initial speed of 125 meters per second at an angle of 7 degrees below the horizontal and hits the target. And the target is on the ground, a horizontal distance of 32.5 meters from the base of the hill. So this is the base of the hill down here. So the target is 32.5. We're just estimating where that is, 32.5 meters horizontally from the base of the hill. Let's draw the trajectory of this pellet. So it's looking like a parabola, and it's going to hit the ground here at 32.5 meters. And the question is asking, what is the height of the hill? So this value up here is what we're looking for. Again, we can choose whatever variable we want to put in that place. I'm going to call it h for height. Okay, so we're looking for the height of the hill. That's it. Step 1's done. We'll move on to step 2. So in step 2 is make a table. All right, so let's draw our table. our table has x and y. And then on the side, we're going to have all the variables from the kinematic equations. So we have S initial, S final, V initial, V final, A, and delta t. All right, so we're going to fill out the table with everything that we know. So let's start by labeling our initial and final positions. This is our initial position. That's where the pellet initially was. Let's label that. So what is that point there? The x value of the point is 0, and the y value is h. Here's our final position. Now what's that point? The x value is 32.5, and the y value is 0. So now that will make it easier for us to fill out the table. S initial, the x component is 0. The y component is h. S final, the x component is 32.5, and the y component is 0. Okay, now let's move on to V. V initial. We have an x component and a y component. We just need to decide which one is the adjacent side, which one is the opposite side. So the x component you can see is adjacent to the 7 degrees. So our V initial x component, it's going to be the hypotenuse, which is 125. Since it's adjacent, we're going to use cos of the angle, 7 degrees. When we look for the y component is opposite of the 7 degrees, so we're going to use sine instead of cos. So it's going to be 125 sine of 7 degrees. Now before we move on, we should double check the signs of these two, whether they should be positive or negative. The x component is pointing to the right, so it should be positive. But the y component is pointing down, so we need to remember to put a negative in front. All right, V final, that's the speed when it's hitting the ground here, or when it's hitting the target. We don't know that value, and we're not looking for it, so we're just going to leave that. Okay, it's not 0, but we don't know what it is, so we're just going to leave it. Acceleration, again, we've said that acceleration points straight down, and it equals 9.8 meters per second squared. The x component of that is 0, and the y component is negative 9.8 meters per second squared. All right, that's it. We don't know what the time is. In step 3, we're going to choose the column that has the most information and solve for time. So which of the two columns has the most information? So if we look, we can see there's this variable here in the y column, h, that we don't know. And in the x column, we do know that corresponding value. So we have more information in the x column than we have in the y, because that h is an unknown value. So we know more in the x, so we're going to choose the x direction. So I'm going to actually just write x direction here to organize myself. Okay, so this is the x direction. We're only focusing on what's in the x direction. So we're trying to solve for delta t. Again, we don't know V final, and we don't really care to find it out, so that's the one variable we're going to leave out. So we're going to use the kinematic equation that does not have V final in it. So that is S final equals S initial plus V initial delta t plus 1/2 A delta t squared. All right, so S final is 32.5 equals S initial, which is 0, plus V initial, which is 125 cos 7 degrees delta t plus 1/2 A is 0 delta t squared. Since there's a 0 in this term, everything multiplied by 0 is just 0, so all of that just goes away. So let's simplify this a little bit. 32.5 equals 125 cos 7. I'm just going to type that onto my calculator. and I get 124.068 delta t. Now I'm going to divide both sides by 124.068. So I'm going to do that on my calculator. 32.5 divided by 124.068, and I get 0.262 equals delta t. So I've solved for delta t. Now let's move on to step 4. Step 4 is now to solve for the unknown in the other column. All right, so now instead of focusing on the x direction, we're going to move on to the y direction. So I'm just going to write that so that we know we're looking at the variables in the y column now. All right, so let's figure out which equation we're going to use. Again, now that we know delta t, we can put that in here, 0.262. It's the same in both the x and the y direction because time is a scalar value. So the x component and the y component are the same thing. We're solving for h, which is our SI. We don't know v final and we're not looking for v final. So we're going to just use the same equation. S final equals S initial plus v initial delta t plus 1/2 a delta t squared. And we're going to start plugging in everything we know. So S final is 0 equals S initial is h plus v initial is negative 125 sine 7 degrees. Delta t, the delta t we know is 0.262 plus 1/2. A is negative 9.8. Delta t, 0.262 squared. Now I'm going to type all of that on the calculator. So I have negative 125 sine 7 times 0.262 plus 1/2 times negative 9.8 times 0.262 squared. So all of that ends up being minus 4.328. Now I'm going to bring that minus 4.328 to the other side, and I get 4.328 equals h. So our final answer is that the height is 4.328, and the units are meters. Okay, everything was in SI units to begin with. Our final answer then will be in SI units as well. So we have a final answer of, it asks what is the height of the hill? The height of the hill is 4.328 meters. All right, so that was question 2. Let's move along to question 3. Question 3. A rifle is aimed horizontally at a target 50 meters away. The bullet hits the target 2 centimeters below the aim point. What was the bullet's speed as it left the barrel? All right, so this question is slightly different than the other two that we've done, but we're still going to use the same process that we described earlier. So we'll start with step 1, which is to draw a picture. All right, so we're going to draw a y-axis and an x-axis. So the rifle is aimed horizontally at a target that's 50 meters away. The bullet hits the target 2 centimeters below the aim point. What was the bullet's speed as it left the barrel? Okay, so let's say the rifle is aimed horizontally at a target. We're looking for that V initial. We don't know what it is. So I'm just going to call it V. The bullet hits the target 2 centimeters below the aim point. So it's going to fall down because it's a projectile. It's only moving under the influence of gravity. That's the only force acting on it. And the target is 50 meters away. So that means this is the target right here. Okay, this is the target. And it's 50 meters away from where you shot the rifle. So this would be 50 meters. The bullet hits the target 2 centimeters below the aim point. So this was the aim point right here. And it hits the target 2 centimeters below it. So if this is 0 down below here, then this must be 2 centimeters up here. So let's convert 2 centimeters into meters. I'll do it on the side. 2 centimeters. We want to get rid of centimeters. We want meters instead. 1 meter is 100 centimeters. When I divide 2 times 1 divided by 100, I get 0.02 meters. So this is that initial height of the bullet. Okay, so the bullet starts off at 0.02 meters above from where it lands. Okay, I'll just write meters here. Okay, some people might choose to draw this a little differently. So a lot of people draw it kind of like this. The bullet starts off here, it's aimed horizontally, and then it will kind of look like a projectile, and it will land over here. This would be 50 meters. This would be 2 centimeters below, so it'd be negative 0.02 meters. And that's totally fine as well. But I know that a lot of people don't like working with negatives, and so I usually recommend drawing your picture so that it's in the positive x, positive y quartile there. Okay, quadrant. All right, so I'm just going to erase this bit here to give us some space. We're going to move on to step 2, which is to draw a table. All right, so our table has columns that are labeled as x and y. And then we'll have a row for each of the variables in the kinematic equations. So we have S initial, S final, V initial, V final, A, and delta t. In my initial drawing, I'm going to go ahead and label my initial position, my final position, and I'm also going to label the points. So my initial position, that point, the x component is 0, the y component is 0.02. My final position, my x component is 50, my y component is 0. All right, so now I'm going to put all of this information into my table. S initial, x component, 0, y component, 0.02. Final position, x component 50, y component 0. V initial, the x component. So it was aimed horizontally, so it only has an x component, and we labeled that speed as just v. So I'm just going to call that v. Okay, the y component, it's only aimed horizontally, so there is no y component to it. It only is moving in the horizontal direction, so the y component would be 0. V final, we don't have any information about, so we're just going to leave that. Acceleration in the x direction for projectile motion problems is always 0, and in the y direction is always negative 9.8. All right, so that was step 2. Moving on to step 3. So So in step 3, we're going to choose the column that has the most information and solve for time. All right, so which column has the most information here? In the x column, there's this unknown variable v, but the y column, we know what that value is for v. So we have 4 pieces of actual numbers or quantities in column y, whereas in column x, we only know 3 values because that v initial, we don't know the actual value for it. We just called it v. Okay, so we're going to start with column y. So in the y direction, we're only looking at the variables that are in the y column. So again, we don't know v final. We're not looking for v final, so we're going to use the equation that doesn't have v final in it. So that's s final equals s initial plus v initial delta t plus 1/2 a delta t squared. Let's plug in everything that we know. S final is 0, S initial is 0.02, V initial is 0, delta T we don't know, plus 1/2 A is negative 9.8, delta T squared. Okay, let's simplify this a little bit. 0 equals 0.02. This term is just 0, and we get minus 4.9 delta T squared. So let's move this term to the other side of the equal sign. 4.9 delta t squared equals 0.02. We're trying to solve for delta t, so we're going to divide both sides by 4.9. And we get delta t squared equals, and I'm going to type this on my calculator, 0.02 divided by 4.9. And I have 0.004082. Now I'm going to square root both sides. With a plus or minus. So when I square root that, I get delta t is equal to 0.0638 seconds. I'm ignoring the minus sign that's in front of there, the plus or minus, because this is time and time can't be negative. All right, so now I know the time. Now I'm going to move on to step 4, which is where I solve for v in the x direction. So step 4, solve for unknown in the other direction. All right. So now we need to choose which equation we're going to use. Again, in the other direction, since we found out what time was, we can put the same time in both the x and the y direction. Since time is a scalar, its value is the same in both directions. So we have 0.06389 seconds in both directions. All right, so we're going to use the same equation as before. S final equals S initial plus V initial delta t plus 1/2 A delta t squared. My S final, now I'm looking at the x direction, I'll just label that here, x direction. My S final is 50. My S initial is 0. Plus V initial, which I labeled as V, delta T, which is 0.06389, plus 1/2, A was 0, delta T is 0.06389 squared. Okay, let's simplify all of this. This term that has a 0 in it all goes to 0, because anything times 0 is 0. And so now I'm left with 50 equals, this is just 0, so 50 is equal to V times 0.06389. Now I can divide both sides by that number. And I'm left with V is equal to, so these cancel out here, so that's why I'm left with V on that side. I just rearranged the two sides. V is equal to 50 divided by 0.06389. And I get 782.6 meters per second. So the bullet's speed as it left the barrel was 782.6 meters per second. All right, that was question 3. We have one question to go. Number 4. In the Olympic shot put event, an athlete throws the shot with an initial speed of 12 meters per second at a 40-degree angle above the horizontal. The shot leaves her hand at a height of 1.80 meters above the ground. What is the horizontal distance that the shot travels? Okay, so let's begin with step 1. Draw a picture. X, Y. All right, so the shot leaves her hand at a height of 1.8 meters above the ground. So let's say this is 1.8 meters. And it's thrown with an initial speed of 12 meters per second at an angle of 40 degrees above the horizontal. So it's above the horizontal this time. The angle is 40 degrees above. So there's my 40 degrees. This is my V initial, and it equals 12 meters per second. Then we just draw the path that the shot is going to take. So it goes up, and then it comes back down, looks like a parabola. And it wants to know what is the horizontal distance that the shot travels. So we're looking for this value right here. We can label it whatever we want. It's a distance, so I'm going to call it D. Okay, I'm going to label my initial and final positions. So here's the initial, and here's final. So my initial position then is 0, 1.8, because the x component is 0, the y component is 1.8. My final position, the x component is D, and my y component is 0. All right, we can also find the x and y for the velocity. For now, I'm just going to label the x and y components here. So this is my x component of velocity. This is my y component of velocity. So now I can move along to step 2. Make a table. So I have x and y. All my kinematic variables. So I have s initial, s final, v initial, v final, a, and delta t. Let's sub in everything that we know. So my s initial over here is 0 in the x direction. My y component is 1.8. My s final is d. My y component is 0. My v initial, so the hypotenuse is 12. When I'm looking for the x component, that's the adjacent side, so I'm going to use cos. So it will be 12 cos of the angle, which is 40 degrees. It's positive because it's pointing to the right. My y component is the opposite side, so I'm going to use sine instead. So it's going to be the hypotenuse, which is 12, sine of the angle, which is 40 degrees. My v final I don't know anything about, so I'm going to leave that alone. My acceleration for projectile motion problems is always 0 in the x direction, negative 9.8 in the y direction. And my time is what I'm going to solve for in step 3. Okay, so let's move right along to step 3. and that's to solve for time. So we're going to choose the column that has the most information. So which column is that? The x column has this variable here, this d value, which is unknown. The y value, the y column doesn't have that, so the y column is the one that has the most information. So I'm going to start with my y direction, and I'm going to use that to solve for the time. So again, we don't know v final, we're not looking for v final, so I'm using the equation that doesn't have v final in it, which is s final equals s initial plus v initial delta t plus 1/2 a delta t squared. And I'm going to substitute everything that I know using just the numbers that are in the y column. So s final is 0, s initial is 1.8, v initial is 12 sine 40 degrees. Delta t is what I'm looking for, plus 1/2. A is negative 9.8. And then delta t squared. So I'm just going to rearrange this so that it's all in the correct order. The delta t squared term should be first, so this should come first. So 1/2 times negative 9.8 is negative 4.9 delta t squared. Then I have 12 sine 40, so I'm going to type that on my calculator. 12 sine 40, which is plus 7.713 delta t, and then plus 1.8. All of that equals 0. Okay, so I can identify here that because I have a delta t squared and a delta t, I'm going to want to use the quadratic formula. My a is the coefficient or the number in front of the delta t squared term, so that would be the negative 4.9. My b is the number in front of delta t, so that's 7.713, and my c is the number that's by itself, 1.8. So let's write out the quadratic formula, which is delta t is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's sub in all the values. Negative b, so b is 7.713, so negative b is negative 7.713 plus or minus the square root of b squared, so 7.713 squared minus 4. A is negative 4.9 and c is 1.8. All of that's under the square root sign, and then all over 2 times a, which is negative 4.9. All right, so I'm going to type this onto my calculator. I'll type it out once with a plus sign and once with a minus sign here. Okay, so we'll start with the plus. So I have negative 7.713 plus the square root of 7.713 squared minus 4 times negative 4.9 times 1.8 over 2 times negative 4.9, and I get negative 0.206. I'll put in a couple digits extra, so 3. And then if I redo the question but I change the plus sign to a minus sign, I'm just going to scroll in my calculator and change that plus to a minus. Then I get 1.7804. All right, so those are the time values that I got. Now I need to decide which of these times make sense. Time can't be negative, so this negative one doesn't make any sense. So the time that it takes for it to go from the initial position to the final position is 1.7804, and that's true both in the x and in the y direction, so I'm going to put it in my table. And now we can move on to step 4. And step 4 is where we solve for the unknown in the other column. right, so using now the x direction. I'm going to solve for the unknown, which is d. Okay, so again, we don't know v final, we don't want to know v final, so we're going to use the equation that doesn't have v final in it. It's the same one we've been using all along. S final equals S initial plus v initial delta t plus 1/2 a delta t squared. My S final, I labeled it as d, so I'm using just the x column here, is equal to S initial, so my S initial is 0, plus V initial, which is 12 cos 40 degrees. My delta t, which is 1.7804, plus 1/2 a, which is 0, delta t, again 1.7804, squared. Now I can just type all of this onto my calculator. So I have 0 plus 12 cos 40 times 1.7804 plus 1/2 times 0 times 1.7804 squared. This term all goes to 0, so I didn't even need to type it. And I get 16.4 meters. So the horizontal distance that the shot travels is 16.4 meters. All right, so I hope that you enjoyed this lecture and that you found these steps to be really helpful. In particular, I find step 1 to be the most important step. Some people try to skip the step, and then it makes step 2 harder to do, and the table ends up being incorrect a lot of the time. So I strongly recommend that you go through the steps, starting from step 1 and all the way through, in order to do these problems. Okay, so I hope that you enjoyed this lecture, and thanks so much for watching. I'll see you again next time.